have Professor Arezoo Hasankhani, who's currently an assistant professor here at UNH, leading energy control and optimization, the lab report. Her research interests include ocean energy systems, control co-design control, and optimization to enhance the use of ocean and blue economy. Prior to joining UNH, she was a postdoc researcher at Cornell University, working on the design and optimization of wave-powered aquaculture farms. She received her PhD from Florida Atlantic University in electrical engineering in 2022, focusing on the design, path planning, and control co-design of ocean current turbines. She is a recipient of the 2021 Graduate Fellowship for Academic Excellence and the 2020 Dr. Stephen G. Schock Scholarship. So everyone give a hand.
Yeah. And do we have the Zoom?
Yeah,
it's
okay.
Yeah, all right.
Okay. So hi everyone. Yeah, my name is Arezoo Hasankhani, and I'm an assistant professor working with the electrical engineering department and also working with the ocean engineering. So today I wanna just present you about the innovations in the design and control of marine energy systems with a specific work with the powering blue economy applications. So to start, I just wanna give you an introduction on myself. I did my bachelor in Iran in electrical engineering, so it was while ago, and then after that I continued my master in the same major, working on the wind turbine. Then for 5 years I was working in the research institute for the wind turbines, and then after that I decided to get back to academia and continue my PhD in Florida Atlantic University, working on the marine current turbine systems for the control and control co-design of this system. After finishing my PhD, I did my postdoc on the wave-powered aquaculture farm in the Cornell University, and since 2024, I'm working with UNH as an assistant professor. My major interests are ocean energy system, control co-design, control and optimization. So here I'm running a lab for the energy control and optimization, or ECO lab. So the vision that we are following in this lab would just improving the ocean energy systems and powering the blue economy applications using the advanced approaches in the control, optimization, design, and control co-design. So that's an interdisciplinary group. We have different expertise from the ocean engineering, electrical engineering, mechanical engineering, and that's all we need for just improving this kind of systems. And we are using advanced approaches like reinforcement learning, like control co-design, machine learning algorithms to just solve the issues that we have with this kind of systems. So if you're familiar with the ocean energy systems or powering the blue economy applications, you probably see these pictures, but for those who are new to this concept, we have a large amount of energy that can be harnessed from the ocean energy. And it can just include different types like wave, ocean currents, ocean tidal, different types of energy. And this amount of energy can just power over 80% of the electrical demand from the US. So we are speaking about large amount of energy accessible in the water. One of the most important applications that we can just imagine for this, for using this power would be powering the blue economy applications. Because using this power somehow is challenging to just transfer this power from the ocean to the shore, and there are some discussions about that. But one of the most important applications here that we can target is using this power to power the applications that we already have in the ocean. Because we have the same issue when we want to transfer power from the shore to that applications. So those applications include the aquaculture farm, just ocean observation, water desalination, different applications that would be called in the powering blue economy application. And it would sustainable use of the ocean. So we want to target those specific applications and use the power that we already have in the ocean to power those applications. So what are the current challenges that we have here? So for the ocean energy systems, the first challenge that we have is a very long procedure for the design of this system. and very costly procedure for the design of the system. To reach the optimal system, you can see from the history of different systems, for example, wind turbine or other systems, it would be a very long procedure for just getting an optimal design. So how we can just make it more efficient? We have different ways, so we can use the control co-design, which is co-designing the control and then the design of the system, considering different parts together and using some advanced approaches to get the efficient design from the system. So we already tested this in different systems, so we can just borrow those ideas and test this for the ocean energy systems. Also, one of the just issues for this system is the discussion on the unsuitability of these ocean energy systems for the final application. So by this final application, we just targeting the powering blue economy applications. So why don't take one step back and then see these applications since beginning? So when we want to design this system, because these applications like aquaculture farm are new in the US, so we can take one step back, see these applications and design and appropriate ocean energy systems to power those applications. So we just targeting two different approaches here. So the design of the system by itself should improve. And then the second approach, we need to consider the final application and just design efficient system for both the application and then the ocean energy system. So two main thrusts I want to cover in today's seminar. The first thrust would be the control co-design for the ocean energy systems, and I specifically speak about the marine current turbine and wave energy converter. And then the second thrust, thanks to the very nice figure from PNNL, so the second thrust would be for the PV applications, and specifically I want to speak about the aquaculture farm, how to just co-design the ocean energy systems with this application. So starting with the first one, and then the first question that we need to answer is, what is this control co-design? So the control co-design, if we want to understand the concept for the control co-design, we first need to understand what is the difference between the control co-design and then the traditional design that we already have for different systems. In the traditional design, you can see that we are starting in the sequential process. So we are starting from aerodynamics, mechanical design, electrical design, electronics, and finally control. So the control would be the final step. What happens if we have this procedure? The control should match all the features that we have in the previous steps. So none of them would consider the requirements that the control have. So what would be the solution for this? We can consider all these steps together at the beginning. So we can consider the control and then the design together at the beginning. And if we are doing this, if we are considering the control requirement and then the mechanical design, it would be the interdisciplinary field that we are interested. We are bringing different expertise together and designing an efficient system which would also answer the requirements that we have from the control. It can also cover other expertise, so we can have the multidisciplinary optimization here, seeing different fields, but right now I'm interested in the control co-design for the control and design expertise. So with this one, this approach is first introduced and used for the airplanes. So we just borrow that ideas. It will be very suitable for the electromechanical system like wind turbines, the marine hydrokinetic devices, and airborne wind energy systems are a good target for using this system, because all of these systems are new systems. So we can use this control co-design concept before going through the prototyping and having so many costs and time, and then getting back to the first step and then improve the design, doing this control co-design and see the improvement in the design at the beginning. So for any system, and here we are interested in the ocean energy systems, what could be the major steps when we want to solve the control co-design problem for this? So the first step is understanding what is our system. It's very important with any system, any new system that you are working with, you need to understand, identify the system and know what is the system doing. And then the second step would be mechanical design. It doesn't mean that you need to just design the complete system, design the controller, go to prototyping, but it means that we need to have a first design for the system. We need to have a basic design for the system, because this basic design is what we are using that in the control code design. In the basic design, we need to consider high fidelity for the design. Why we need this? Because we want to just play with the design variables in the design and change this with the control requirements. The next step would be understanding what are the control requirements for our system. Which control do we need for our system, and then what are the main requirements for them? So after that, we can just couple these two together and then target the control code design. So we are doing the control code design, but for doing the control code design, we need to know what would happen in the design of the system and what is happening in the control of the system. So I first start with giving you an example from what I did in my PhD. So it was the system that I designed in the PhD. It was a marine current turbine, 700 kilowatt marine current turbine designed for the Florida Gulf Stream. It can be used for other locations, but it's originally designed for that location. So you can see that this system has the buoyancy to change its operating depths. So what are the main components for this system? We have the variable buoyancy chamber, which is responsible for moving the system vertically. Because for the marine current turbine, for the ocean currents, the speed of the water is changing in different operating depths. So we need some sort of technologies to change the operating depths of the system. And here we are using the buoyancy. We also have the main body, which places the generator. We have the rotor, which is responsible for generating the power, and mooring cable, which is used to attach the system to the seafloor. To better understand how this system is working, I show you this animation. You can see that the vertical position of the system is changing. So why we are changing the vertical position? Because we want to put the system in the locations with the highest ocean velocity. So one question that we are facing here is, if we only are targeting to put the system in the highest ocean velocity, what is the optimization problem here? Because we already know what is the ocean velocity, and then we can place the system in that one. The answer to that is, we don't only generate power with this system. We need to consume some power to just hold the operating depths, because the velocity is changing, and we need to consume some power to change the operating depths. So the optimization problem here is necessary to find the balance between the power that we are generating from the system and the power that we are consuming with this system. So with this introduction, we designed the system, we simulated the system, and now we want to see what are the just operation of the system in 3 different conditions. So the first condition, homogeneous flow and shear flow, very simple condition in the ocean. We want to understand what is the range of application for this system. This can give us what are the range of operating depths that we can achieve with the system. The next part would be some faulty conditions. If we have the rotor stop, if we have the pitch imbalance, what would happen to our system? If our system can resist, or something very unusual would happen to the system. And we see that our system can resist to those faults. And finally, seeing the operation of the system for the oceanic, real ocean velocities. So for the normal conditions and hurricane conditions, seeing what are the power output from this system and what are the location of the system. So we understood that the first design, the basic design for this system, is working very well in different conditions. So with this just intro, we have a very detailed and nonlinear model for this system. If we want to use that nonlinear complicated model, I didn't show you the equations for that one, but if you're interested, we can discuss about that. So if we want to use that complicated model, we can do that. but we are targeting the control co-design. The control co-design wants to just place both the control and design of the system. If we want to put both of them in very detailed approach together, it would be very time consuming. So if we can linearize or simplify the design of the system or the control part for the system, we can just make this system faster. So the first attempt for linearizing the system, we just get the linear model from the vertical movement and linear model for the power generation from the system. And then justify those models with the nonlinear model and see that the precision is enough for our case. So for the linear model net power, you are seeing here that we have the net power from the system. I already explained it. Here that we have the power production, which is coming the ocean current velocity, and then we have two terms for the power consumption for this system: power to hold the operating depths and power to change the operating depths. So we need to see the balance between these three terms to find what is the maximum power that we can get from this system. So after understanding and finishing the design, the first step is done. The first two steps is done. We already know the system. We already designed the basic system. And now we want to understand the third step, which is just the control that we required for this kind of system. For this system, as we discussed, we need the path control. We need to control the operating depths for the system. So the path control by itself has two levels. The first one is the path planning. We need to understand what is the optimal path to maximize the harness power. And then the second part would be path tracking. We need to add some controller to the system to track those optimal paths. And we need to make sure that the actuators in the system are capable of tracking those paths. So to give you better idea on how this system would be different, how the power just harnessed from the system would be different, if we have the static MCT, which is operating in only one operating depth, with the dynamic marine current turbine, which is changing its operating depth, after only 100 hours of operation, we can see 20% increase in the ocean, in the energy harvesting. So it's very important to just apply this kind of advanced technologies for the controlling this system. So the first task I don't want to go over the formulation, just showing you and giving you some ideas for the path planning. The first idea is just using this system and targeting this system as the autonomous underwater vehicle with the primary role of energy generation. Why I did that? Because by doing that, I can borrow the ideas in the robotics. I borrow the reinforcement learning algorithm and then apply on this system for the first time and see very good results from this system. So you have different approaches to solve this optimization problem. We want to maximize the harness power. We have some uncertainties in this system and we need to find out what is the solution. You can apply different approaches. I tested model predictive control and reinforcement learning, and reinforcement learning show a very good performance because we have too much uncertainties in the ocean. So the reinforcement learning, adjusting this problem to that one and then seeing the results from that one. So it was very good for the path planning. The next part, the path tracking, we want to make sure that actuators from the system is capable of tracking those paths. So don't be afraid from this equation, it's just the model predictive control. So for tracking the optimal path, we want to make sure that the error when we are tracking that optimal path would be minimum, and then the model predictive control would be very good. Even PI controller is working very well for this tracking controller, but the only problem here is just addressing those uncertainties. Just seeing those uncertainties for the system. And we make sure that our system is capable of tracking the optimal path that we already got from the path planner. So now we know the part for the design of the system, we know the part for the control of the system, and we are ready to just apply the control co-design. Getting back to the first objective from the control co-design, we need the control co-design for this kind of system to make sure that the path control and then the requirement from the path control would be seen at the beginning. Since the beginning, we designed a system that is capable to just harness the maximum power and then following those optimal paths. So we use the control co-design and then just design the system and see how this control co-design changed the basic design that we had since beginning. So for this one, we can just target changing different design variables in the system. But for my case, I just targeted three, the rotor of the system, the buoyancy tank, and generator. So these are three main design variables that I targeted in the system to just see if we are changing these three variables, how the design of the system would change, and how the power to weight ratio, which is our objective, would be affected. So the rotor is very important for generating the power. The buoyancy tank size would define how much our system is moving in the vertical position, and then the generator shows us the rated power that we can get from this system. So with this, just choosing these three variables, now we want to just define the control co-design approach. The control co-design approach should oversee the objectives from the design of the system and then the objectives from the control of the system. So we have two levels here. We need to just combine these two levels. How to combine these two levels? It's the art that we have here for the optimization. In my problem, I just define this framework to consider the outer optimization loop, which is for the design of the system, and then the inner optimization loop, which is for the path control of the system. So we are considering two different optimization loops. You are seeing that the problem is getting more and more complicated, and now you can see why we need to simplify the model wherever that we can. So the main problem for we already see the path control problem. The main problem for the outer optimization would be maximizing the power to weight ratio. And then we are changing different design variables here, which are the rotor, generator, and variable buoyancy tank size. So the problem here, maximizing power to weight ratio, and we need to see if we are changing the rotor, generator, and variable buoyancy tank size, how the mass of the system would change. By changing all these parameters, how the mass would be changed, and we need to formulate them. So after just formulating the problem, we want to see what are the results that we get from here. So the first case we show here is the base design. So the base design, we only apply the just path control to the base design that we have since beginning, and we see what is the value for the power to weight ratio. Then we tested this with the sensitivity analysis. We understood that the rotor diameter is the dominant design variable here. So the second case is showing if we only just target the control co-design for the rotor diameter, what would be the changes? So you can see that the rotor diameter size is increased, and you are seeing around 16% increase in the power to weight ratio. And then the final case is changing all of the design variables, rotor diameter, generator size, and variable buoyancy tank size, and seeing how this impacts the power to weight ratio. And you are seeing around 18% increase compared to the first case. Now we can understand how much this is important to apply this control co-design approach for this kind of system before going through the prototyping and before spending so much time and money for this system. So with this intro, what is happening now in Ecolab? What is happening now in our lab? We are working in the control co-design coupled control, optimization, and design for the wave energy converter. So again, we need to understand we are working right now with the point absorber type of wave energy converter. We need to first understand what these systems are doing, and then we need to understand another part for this system, which is power takeoff technologies to just harness the power from these systems. And then we need to have the mechanical design with high fidelity because we want to play with them in the control co-design, and then understand the control requirements from the system. For example, I show you here that for this system we need 3 control blocks. The first control blocks for the maximizing the capture power, and then then limiting the force from the PTO, and then the two other blocks which are related to just controlling the power output from this system. So we need to consider these control requirements from the beginning and control co-design for this system. So with this, I wanna just switch gear and then go through the second thrust, which is co-design of the ocean energy systems for the powering blue economy applications, specifically aquaculture farm. So the first thing here is just clarifying, is this systems, is wave energy converter a good option, and can it power the aquaculture farm? So the first thing is we are going further offshore for the aquaculture farm because there is a high competition in the near shore zones, and then we want to just avoid those competitions. And also by going further offshore, we can just increase the amount of production from the aquaculture farm. So the current energy need from the offshore aquaculture farm is met by diesel generator. You may have the question, what are the energy demand from the aquaculture farm? It's an example here. So for the lighting, for the feeding, for other applications, we need some power for the aquaculture farm. And then with this one, we are seeing, for example, for this example aquaculture farm, we have around 2,800 megawatt hour for 10,000 of fish production. So with this amount, we can just get the initial guess and just compare them with the annual energy production that we have from a sample wave energy converter. Reference Model 3 is a very well-known wave energy converter designed by Department of Energy, and then the targeted annual energy production for a specific location that they just evaluated was estimated around 700 megawatt hour. So if we just roughly compare these two values together from very rough comparison, we can get that for reference Model 3 would be enough for powering this system. We don't go over the details yet, but just seeing the amount of power that we can get from the wave energy converter, and then the amount of power that we need for powering these systems. So it shows us that it is feasible to use the wave energy converter to power this system. Now we need to just go over the design, consider the requirements for the system, how to design the wave-powered aquaculture farm. So for just doing this, we have different steps here. So the first one, that if we want to have the wave-powered aquaculture farm, the problem gets even more complicated. Because when we are speaking about placing something in the ocean, the first thing that we have in our mind, we have too many activities happening already in the ocean. So the first task is the mapping tool that shows us what are the available options for us. Which option, which location would be available for us. And why do we need that? Because these systems would be designed for a specific location. Because we need to know what are the available wave energy from those locations. What are the available parameters, environmental parameters for those locations. So we need to know what are the locations that we can do those activities. And then just conceptual design of the system. What are the main requirements from the aquaculture farm? What are the main requirements from the wave energy converters? Because these are two separated systems, and then we need to combine them together. And finally, optimize the wave-powered offshore aquaculture farm together as a single system. So I just again give you some results from my postdoc research, and then going back to the research that we are now doing in the Ecolab. So the first task, as we mentioned, we need to select the deployment location for the wave-powered aquaculture farm. To do that, we need to just consider different considerations. The first one, environmental factors. The environmental factors are important for both fish and then wave energy converter. We need to consider what is required for the fish, temperature, salinity, dissolved oxygen, and current speed, and what is required for the wave energy converter, significant wave height and wave energy period. And then we want to avoid the conflicts with other activities that are already happening in this area. And finally, we want to maintain the ocean health of the fish. So we want to just place the aquaculture farm in the location that we are sure that we can get production from. So giving you another example, these are the activities currently happening in this area. So some of them we cannot enter those areas definitely, and then some of them are just are not red flag. We can just collaborate with them. But knowing all the activities that happening in this area is very important, because we want to place the offshore aquaculture farm and wave energy converter, both of them in the locations together. So we need to understand what are the activities happening in this area and then place our system. So after just addressing the first part, which was the mapping tool and understanding what are the locations that we have available for this system, then we want to start with the conceptual design. So what are the main components for the system? We have two main components, wave energy converter and aquaculture farm. So for wave energy converter, what are our targets? We want the minimum cost, high reliability, and because we are targeting the offshore aquaculture farm, we need a near constant power supply. And then for aquaculture farm, again, minimum cost and then maximum fish production from this system. So what are the components here? So the wave energy converter, we need to consider what is the energy generated from this system, and we need to also model the cost of the system. For the aquaculture farm, we have net pen, feed barge, fish type, and carrying capacity. So for the net pen, it is very important to know the geometry of this system. Because if we know the geometry, we are designing this system, we want to see how the design of the system would change. And then the materials that we are using here, the energy required, and again, cost that we required for this net pen. And feed barge, we need to know how much energy we required for the feed barge, and then what is the cost for this system. The fish type, I was working with the Atlantic salmon, so the fish growth model, if you are putting some fish and then you are considering the period for the growth of them, what would be the final weight that you can get from them? So we need to model the fish growth for this system and also the dissolved oxygen consumption to make sure that it is a healthy environment for the fish. And the carrying capacity give us some understanding on what is the limit for the amount of fish that we can put in the net pens to make sure that we have the healthy ocean environment. The offshore environment, we have the temperature, current speed, dissolved oxygen, salinity, which are required for the fish, and then significant wave height and wave energy period required for the wave energy converter. And finally, we need energy storage for any type of renewable energy system. We need to combine them with the energy storage to increase their reliability. So, and then we need to know the energy model for that system and cost model. So you already see that we have a very complicated model here. So we need to model different parts and see the relation, the coupling between these different parts together. So just to give you some ideas, again, I don't want to go over the equations, so I just give you some ideas. The energy model for the reference model 3 that we were working previously was we all have the annual energy production for this system, what is the power generation based on the wave height and wave period that we have. And for the net pens, we need to understand what is the fish yield for that system based on the amount of stocking density that we are putting in just net pens, what is the annual energy consumption, and what is the carrying capacity, which gives us the limit for the amount of fish that we are putting in the system. So after modeling all these components together, and I didn't go over the rest of the components, after modeling all these components together, because it's an ongoing research, we need to just model the objective function again, solving an optimization problem. So we are always solving an optimization problem. Solving an optimization problem right now for minimizing the total cost of the system to fish yield. So seeing what is the cost that we are giving from the system based on the fish yield that we have from the system. So the constraints that we considered at the first try was the power supply, make sure that it is enough to power the aquaculture farm. The fish yield, make sure that the fish amount of fish that we have here would be just in the range of carrying capacity, and also just putting some ranges for the net pen geometry. And then by this one, we just have the design variables here, which are the capture bits for the wave energy converter, giving us some idea from the physical design of the system and also the diameter and height of the aquaculture farm and then stocking density. So these were the first trial with this complicated model and seeing what are the results. So the first results that we get from here, so with that model, don't go over too much details. We just understood that the optimal designs that we expect from this system we can have different design, but all of them, the capture widths from the wave energy converter and then the pen volume should have the ratio of 0.003. And then we have the optimal stocking density of 20 kilogram of fish per volume. And then the optimal cost per fish yield was $6.4 per kilogram of fish. But this model was not complete because we didn't go over the details for all the components. It was only the first trial. And after seeing this, we understood that we need to go over the details for all the wave energy converters, all the energy storage system to have a better results here, to see the better cost estimation here. And this is ongoing work. We are working on that one to just see what would be the complete model for the cost of this system and seeing some comparison between this cost and cost from the diesel generator option that we have. So it just highlights for us that we have required to optimize the design and location simultaneously. And also we need to have a detailed design from the wave energy converter and aquaculture farm together. So now what is happening in the ecolab? The second part. We need to design a wave energy converter reference model which can be useful. Now we know that we need a detailed design for the wave energy converter. So why we don't have a reference model wave energy converter which is targeted the PV application? So this reference model need to be with high fidelity, which we can play with that one and just make it suitable for different PV applications. And our first target is with the offshore aquaculture farm application. So the PTO technology for these systems, I also mentioned that the PTO technology is very important. We started with the two-body point absorber, and then we need to understand what are the power takeoff technologies for this system. So for doing this, we need to just combine the simulation and then the design for the lab testing together and seeing with this high fidelity model, if we want to do the modeling, if we want to test it in the wave tank, and then if we want to go over the field testing, how this design is changing and how we should justify this for the offshore aquaculture farm. And all this information help us to just understand how to design an optimal wave-powered aquaculture farm together. So, and then to give you some feeling on that one and just intro on the research that we are doing. So the wave energy converter types that we're having, because I didn't speak about this in this presentation up to now. So we are targeting point absorber, oscillating water column, and oscillating surge wave converter. And then we have 4 different types of the power takeoff technologies. And again, I don't have time to go over the details for that one, but these are the models that we consider. Why do we consider these models? Because we want to know what are the selection, what are the good pair between these wave energy converter types and then the PTO types to power the aquaculture farm. And we did it for different PV applications, but right now I only show you the aquaculture farm. And after seeing those results, we can make decision on which pair we want to work for our research and then start working on that one. So for example, for the offshore aquaculture farm, we do understand that the oscillating water column is working very well with the 80 PTO options. And then we are seeing that the point absorber is probably the best choice here. And it can work with the mechanical direct drive, electrical direct drive, and hydraulic based system. And then when we want to choose them, we need to just see the considerations that we have here. What is the efficiency for this system? What are the considerations here? And just choose the right system for our type. And then the final choice is not good, because if we are speaking about the offshore aquaculture farm, if we are going further offshore, this option is not very well for our case. So with this approach, what I have in my mind and what I'm seeing as the research for just leveraging different control, optimization, and design perspectives is just designing a toolbox for the Ecolab, and this toolbox is just targeting to use different approaches for the control, design, optimization, co-design, control, co-design, and multidisciplinary optimization. So do we need to use all of them always? No, it's up to the problem. You are seeing already two different problems. So one of them was for the design of the ocean energy system. One of them was for the design of the wave-powered aquaculture farm. So we have the different oceanic data here for the ocean current velocity, significant wave height, wave energy period, any oceanic data that we have. The quantifiable metrics, economic, security, technical, or environmental. And then the disciplines that we have, the control, electrical, mechanical design, ocean engineering, any disciplines that we are interested. So then when we are targeting a specific problem, for example, we want to see the new optimal design for ocean energy systems, the wave energy converter, we need to just use the control, design, and control co-design. So this gives us the ability to have a good design for this system. When we are targeting the existing system, the reference model tree, and we want to improve the design of that one, the control co-design and multidisciplinary design optimization can help us. When we are just considering the optimal array for the system, the optimization task would be enough, and they are very close to each other. We can use these approaches in different problems. And finally, if we have the ocean energy systems powered applications like wave powered aquaculture farm, we can use the concept for the co-design for this system. So seeing all of them together, we can target different problems and then can use different disciplines to solve these problems. Finally, to just have the efficient ocean energy systems, we need to just borrow different ideas for the advanced technologies for the design, optimization, and control. So couple design, optimization, and control are the key to improve this system. We cannot go over the sequential design, we cannot go over the traditional design with the hope that we can just make this system efficient. And then the PB applications, if we need to just justify that these ocean energy systems are good for the PB applications, we need to take one step back and just design the system specifically for that PB applications. So, and then we need to just use the co-design perspective and then all the optimization techniques that we discussed. So, thanks for your attention.
Thank you so much. That was really great. I'd like to open for questions if anyone has any questions for this speaker.
So one question that I have is, for your model, I was curious to know how you are obtaining that information about the wave velocities, as well as how much noise is creeping into that model that could affect the control system as well, and how you deal with that.
Yeah, so you are
Slide 13. 13 or 12. Yeah.
this one, 13, this one, there, this one.
It was the one with your original work that you did. Yeah, that one.
This one?
Yeah.
So it was the measurement that we have for the Florida Gulf Stream. So it was the real measurement. So for getting this data, the best, the data is the key for doing this kind of researches. So you need the real data, and here in UNH we have this data. So you can use those data and then you use those data for your research. But if you don't have those data, it would be very difficult to do that research. And I didn't work on the noise of this system, but it's also another aspect, another discipline that we can add to this system and see if we are just considering the noise, what would be the impact on the, ocean, just what would be the impact on any fishes, anything like this. Yes.
Nice animation, thanks, Arezoo. What is the timescale? What?
It's hour.
Just, that's 1 hour from left to right?
No, it's not 1 hour, it's just hourly scale for that one, but I don't put it here. I believe that it's because the time is changing. It's
Yes, I
moving
just
with the
wondered
time.
How
Yeah.
fast the currents are changing.
Yeah, I don't have this on top of my mind, but yeah, I can check that one for you. But the time steps that we considered was hourly time step, and it was not changing so fast, but it's just changing and then
It looks like days to me, like 12 hours to days kind of things, where you're seeing that variability.
Yeah, so all of this would be around 24 hours. So the range of this would be 24 hours, but it's the window that is moving. So it's just showing you maybe 48 hours,
So the
something like
device
this.
adjusts relatively slowly.
Yeah.
Since we're here, can you go to slide 13, I think is when you talked about the reinforcement learning?
This one,
No, one more.
this one. Yes.
That one.
Yeah.
So I don't think I understood very well. So you're using reinforcement learning for path planning in the simulations that you have with the currents, and then the PI control for the following, the path
The
following.
MPC. Yeah.
That's you calculate the path planning with the reinforcement learning, and then the actuators try to keep it within that path with the PI controller.
Yeah, so if you want to, just keep going. That's a good question. Here. So you're asking about this one.
Yeah.
So just relation between these two. The path planning, I tried different approaches. For the path planning, I tried MPC and reinforcement learning. Reinforcement learning was working very well because these ocean current velocity data are uncertain. And then we are seeing the path tracking controller with I tried the MPC and then just compare it with just the PI controller. I also tried reinforcement learning, but reinforcement learning is not very good for the path tracking controller because for controlling the actuators, the problem does not have that much uncertainty to just use the reinforcement learning. So MPC or just the even PI controller is working very well. So these path planning, finding out what is the optimal path, and then giving these to the path tracking controller, we are looking to the one horizon. So for example, 24 hours ahead of time. So it's just finding out the optimal path and giving this to the path tracking controller and just understand what are the actuators, what should be the actuators value to just get those optimal paths. But in the path planning, we consider some limits related to the actuators to make sure that the value that we are giving to the actuators it's in their range because we know that how much can get from those actuators.
And what you're trying to reinforce is maximum power, maximum energy.
Yes.
Okay.
Yeah.
Okay, thank you.
And in regards to MPC, you're talking about model predictive control.
Yes.
And how are you setting up the models using the predictive control aspect for path planning?
For the path planning, so it's very, for the path planning, the model predictive control and the reinforcement learning, both of them are working with the same problem. So with just maximizing this harness power and then considering one horizon for the system. And then the difference between them is how to solve the problem. For the reinforcement learning, we are defining the environment, the states, the actions for the system. For the model predictive control, it's easier because it's similar to the traditional control problem. So we are giving this problem to that one and then just seeing the constraints for the system, just defining the constraints and having what are the variables here and then finding out what is the optimal path that we get here.
So you're practically adjusting which parameter then? Are you adjusting just like the Z and B, or are you adjusting your error rate for the output component?
No, we are getting the value, so we are just adjusting, so it's just called the economic model predictive control.
Okay.
So we are just going to do, it's similar to the optimization. So the next one, the model that you are saying is similar to this one. It's for modeling, it's the original and traditional way of the model predictive control, so for minimizing the error. For this one, it's usually more close to the optimization. So we want to understand what is the optimal path here.
Thank you.
Any more questions?
So this might be a really dumb question. But you started talking about optimal costs in dollars per kilogram of fish. Where do you want to be to make that an improvement over what farmers do now? What is the kilograms per fish that you're shooting for? Dollars per kilogram fish, I mean.
Yeah, so you mean that what is the
In a practical sense, where are we headed with that?
yeah, so it's the
How close are we to getting to?
yeah, exactly. So that's a very good question. The number that we get from the farmers for the it's the number that I'm saying. So it's changing a lot. I remember this from it's for 1.5 years ago. It was around $6 per kilogram. So we were close to that one. But again, this number that I reported here, it's not for a detailed cost model. So the detailed cost model probably increases this value, and then again we have some increase in the value of the fish. But for that specific number, the value for the market was $6, so we were close to that one.
Okay, yeah, thank you.
Okay. Do we have any questions online? Oh, thank you very much.